Hi math lovers, in this video we're going to be looking at a pretty interesting problem that I saw off the internet and I decided to make a video on it. So we have this problem: prove that there is no triple of positive integers x, y, z which satisfies the equation x squared plus y squared plus z squared equals to x, y, z. So let's look at this equation in a bit more detail. Now over here we have a 2. This implies that the right hand side is always going to be even no matter what. And the only way in which these two sides can be equal is if the left hand side is also even, right? So I suggest that the only way the left hand side can be even is if all three of these variables are even, or if 2 are odd and 1 is even. And I'm going to prove that just right now. So if all three of them are even, it's pretty obvious that their sum will also be even, because if I have, say, 2j whole square plus 2m whole square plus 2n whole square, then that will give me 4j square plus 4m square plus 4n square. And since each term is divisible by 2, then the whole thing also has to be divisible by 2, right? Now, if we have two odd integers, so we have, let's say, x equals 2j plus 1 and y equals to m plus 1, while z equals just 2n. So we have 2j plus 1 whole square plus 2m plus 1 whole square plus 2n whole square. And this simplifies to 4j square plus 4j plus 1 plus 4m square plus 4m plus 1 plus 4n square. And these ones all add up, and this gives us the final answer: 4j square plus 4m square plus 4n square plus 4m plus 4j plus 4n plus 2. And again, you can see that each term is completely divisible by 2. So the whole thing is also divisible by 2. Now that we've shown that, the original equation we had was x squared plus y squared plus z squared equals to xy. Alright, now this is the part where practice is pretty important. Over here you have to make a substitution, and the substitution is that let x equal 2 raised to k into x prime, where 2 raised to k is the greatest common divisor of x, y, z, which is also a factor of 2. And similarly, y also equals 2 raised to k into y prime, and z also equals 2 raised to k into z prime. Now let's substitute these new variables into the equation. Now let's see what we get. So we'll have 2 raised to k into x prime whole square plus 2 raised to k y prime whole square plus 2 raised to k into z prime whole square equals 2 into 2 raised to k into, actually let's not use a cross here because we already have an x, so 2 raised to k x prime, 2 raised to k y prime, and 2 raised to k z prime. Now if we expand this, we'll end up getting this expression: 2 raised to 2k x prime square plus 2 raised to 2k y prime square plus 2 raised to 2k into z prime square equals 2 raised to 3k plus 1, because all of the k's add up, as we know from the laws of indices, into x prime, y prime, z prime. So let's try and simplify this equation a bit more. It's actually pretty long to write it. equals to 2 raised to 3k plus 1 x prime y prime z prime. And now, if we take out 2 raised to 2k common on both sides, we get 2 raised to 2k into x prime square plus y prime square plus z prime square equals 2 raised to 2k into 2 raised to k plus 1 into x prime y prime z prime. And now, if we just cancel off these 2 raised to 2k's, then we'll end up getting an expression kind of similar to the original one, but not quite. X prime square plus y prime square plus z prime square equals 2 raised to k plus 1 into x prime y prime z prime. Alright, now, here's the part where you have to think quite a bit. So, over here we have 2 raised to k plus 1 and x prime y prime z prime. So this side is, again, it has to be even. And the only way this side can be even is if we have 3 even integers on this side, or 2 odd and 1 even. Now if we have 3 even, then that would imply that x prime equals 2 into j, y prime equals to m, and z prime equals to n. So at the very least, these 3 integers are gonna have a common factor of 2 between them, right? I mean, I can divide all of them by 2. And since we assume that k, let me just write it down again. 2 raised to k is the greatest common divisor of x, y, z, which is also a factor of 2. So this is what we assumed in the start when we brought in 2 raised to k. And so this is just not possible. So we'll reject this, and instead let's look at the other option. So the other option is that x prime equals 2j plus 1, y prime equals 2m plus 1, and z prime equals 2n. And I know that some of you are gonna say, hey, there's 3 integers, why don't you take z as odd and y as even? But it doesn't really make a difference, as we're gonna see. So we have x prime square plus y prime square plus z prime square equals 2 into k plus 1 into x prime, y prime, z prime. And if we substitute in the new values for x prime, y prime, and z prime, we get this: 2j plus 1 whole square plus 2m plus 1 whole square plus 2n whole square equals 2 raised to k plus 1 into x prime, y prime, and z prime. Now if we expand this out, we get 4j square plus 4m square plus 4n square plus 4j plus 4m plus 2 equals 2 raised to k plus 1 into 2j plus 1 into 2m plus 1 and into 2n. And now if we look at this closely, it's pretty obvious that when I divide the left hand side by 4, I'm gonna have a remainder of 2 left over, right? And if I divide the right hand side by 4, I'm not gonna have a remainder of 2 left over, because I have a 2 raised to k over here and I have a 2n over here. So if we multiply both of them, what I'm gonna get is 2 raised to k plus 2, which is just 2 raised to k times 4. So this entire expression is going to be multiplied by 4, which means that it's going to be divisible by 4, and therefore we have a contradiction. This cannot be possible. Hence we have proved that there is no solution to the original equation x squared plus y squared plus z squared equals to xyz. Thanks for watching this video. Please like and subscribe. Have a nice day.